Hello everyone, Mr. Mike's my name. Math is my game. So, today what we're going to do here in a minute in this video is review for the Chapter 6 stats test. Let me just stop this YouTube thing that's playing. Sorry about that. Okay. So this is going to be information on that 35 question Chapter 6 test. The general shape of a normal curve. Remember what the normal curve looks like? It looks like that approximately. And we did kind of say that that's supposed to be like a bell, okay? If you could picture what a bell looks like. Ding dong, put a handle on it. Okay, it looks like a bell. You need to know the definition of a mean. Remember, the mean is a mathematical average. Definition of standard deviation. Some people confuse the two because standard deviation is really the average distance that something is, or the average deviance, how much something differs from something else in a data set on average. Okay. Normal curved, what's that mean to have a normal curve? Well, it's a bell-shaped curve. What determines both the height and width of the bell for the normal curve? Well, we had talked about that a while ago. What determines the height and the width? Well, remember the center of it. The center of it is usually based around the mean, and for a standard or for a normal distribution, the mean is 0. If we had an average of negative something, well, the bell would be down here, and if it was positive something, the bell would be up here. So anyway, the mean doesn't really affect the height of it, it just affects the location. What affects the height is the standard deviation. Let's think about this. Suppose the standard deviation is 1. Okay, if the standard deviation is 1, well, then we'll have a curve that kind of looks like this. Okay, if the standard deviation were much larger, suppose it's 5, well, what's going to happen is that curve, it's still going to have its peak in the center, but that curve is going to be much wider because the data is more spread out, because on average, one item differs from the next by 5. Okay. Contrastly, if the standard deviation were small, let's say it's 0.1, the data is not very spread out at all, and so the bell would look something like that. Okay. All right. Correlation in a normal probability plot. Remember the normal probability plot? We took the z-scores and something else, and we kind of plotted them like this. And no matter what, as the value goes up, so does the z-score. So we should expect those to always have a positive correlation. Now, in the event that we were to flip those axes around, the graph might look a little bit different, but either way, and I don't know if you remember this when we did it on the TI Inspire, but either way, there's still going to be a positive correlation, even in the event that we flip the axes. In other words, if we flip the independent with the dependent variable, it's still going to have a positive correlation, okay? On the one quiz, you were asked to come up with a variable that's normally distributed. Some that we had thought of that we discussed in class were heights of people, standardized test scores. That's a standardized test, well, the SAT, for instance. What's a variable that's not normally distributed? Something that's going to be highly skewed. You know, where some people, where there's going to be, I don't know, some people or some items that are much higher or much lower than others. So check your notes on those. That quiz, hopefully you'll get that essay quiz back. Where does the density curve lie? So that's an interesting question about that density curve and where it lies. In the notes, we said that it lies on or above the horizontal axis. So, in other words, the density curve actually does touch down. It actually does touch down. Okay, the density curve actually does touch down. Okay. How does the mean affect the curve? We talked about that. How does the standard deviation affect the curve? We talked about that. Let's see, z-scores. something about z-scores. What is it that you need to know? With the z-score, the formula to calculate a z-score, remember, is the item minus the mean over the standard deviation. So let's suppose we are 68 inches tall and the average is 70. And we divide that by the standard deviation, which is 1.3. In that case, think about what you're going to get for the z-score. Think about, does that make sense? If average is 70 and we get a z-score, that z-score is going to be less than 1. Is that allowed? Does it make sense? Well, sure, it's allowed. It just means it's less than average. Okay? And that's okay. Z-scores are allowed to be negative. Remember, the table had two sides on it. Speaking of the table, when we found an area like 0.99375, whatever, what that area means is that's the percentage of the stuff, that lies to the left of a certain z-score. Okay, that would be a certain z-score, something high like 2 or 3 or something. But it's the area to the left of that z-score. Okay, you need to know that. Suppose the z-score is negative 1.76. Let's find the area to the left of the curve. Well, I would need my table for that. So if I look up in my table, negative 1.76, I get 0.03920, 0.03920, 0.03920. And that's right in the table there. Okay? What's the difference between the empirical rule and the table? If you remember the empirical rule, it says that 68% of the data lies within one standard deviation of the mean. Within one standard deviation of the mean. Okay? That's what it says. If we use the table, what we'd have to do is go to negative 1, and the area for negative 1 is 0.15866, 0.15866. And then we go to positive 1 in the table, and there we get 0.84134, 0.84134, 0.84134. And if we were to find that difference, in other words, find the area according to the table that's in there, the empirical rule says it's 68%. The table is going to differ by a little bit. Not much, but it is going to differ. The table says it's 68.268%. Okay, so the table and the empirical rule say almost the same thing, but the percentages are a little bit different because of rounding and what have you. Okay. If we think about a z-score of 0, what does that mean? If the z-score is 0, if the z-score is 0, what percentage of the data lies to the left of that? 50%, half of it. If the z-score is 0% lies to the right of that, lies to the right of that. Well, that would also be 50%. Okay, and if you look at 0 in the table, it says the area to the left is 50%, and so there you go. Okay. Multiple ways to find a z-score. Multiple ways to find a z-score. So suppose we wanted not to find a z-score, but to find the area to the left of a z-score, let's say. Let's take a look at one of these. Because there's more than one way to do this. Suppose we had a z-score of 1.58. Z-score 1.58. And we wanted to know the area to the left of that. Okay? So we could go to the z-score of 1.58 and look up in the table. And we get 0.94295. 0.94295. 0.94295, if I did that right. 1.58. Yeah. Okay. Now, so that's for a z-score of 1.58. Another thing I could have done is if I had gone to the z-score of negative 1.58 and looked up that area, that's going to be 0.05705, 0.05705. So if I took 1 minus 0.05705, I actually get the same thing. So I don't know if you noticed this or not in the table, but in the table, the positive z-scores and the negative scores are in effect each other's complement. So what we could do to find the area under a table is just, look it up in the table, or take 1 minus the area for the z-score that corresponds to the opposite z-score. Okay. So there's more than one way to do that. Assessing normality. Why is that so important? Well, in statistics, if you recall, in order for inferential statistics to occur, to take place, for the calculations to be valid, we assume that the data are normally distributed. Okay. When do we use normal probability plots? Hopefully you remember that one. We use those normal probability plots if the sample size is relatively small. Okay. Finally, find a quartile given a mean and a standard deviation. So suppose the mean is 5, standard deviation is 1. Find the third quartile. So we'd go to the z-score that corresponds to the third quartile. So third quartile separates the lower 75%. So that's going to be a z-score of 0.67. Okay. So what we've got then is z equals mu minus x minus mu over sigma. So 0.67 equals x minus 5 over 1. So we would get 0.67 times 1 equals x minus 5. So x would equal 0.67 times 1 plus 5. So that's 5.67. Okay, 5.67 in that case. And you did those in the exercises, so there will be a question like that on the test. So that's it. That's been real. It's been fun. I hope everybody gets a great score on this Chapter 6 test. It is Scantron. It will be Friday. Have a great day.